Hello, welcome to the third and final part of section 8.7. I'm just going to go over a bunch of very interesting examples, okay? So let me start by showing you the table, a table of Maclaurin series. The first one here you probably recognize is just a geometric series. This one we computed. This is e to the x. Sine of x, we also did cosine of x we got by taking the derivative of sine of x. Then here I'm giving you tangent inverse. You've seen the power series expansion of the natural log of 1 plus x, and this is the one we did at the end of my previous video. Let me remind you that this is good for absolute value of x less than 1. Okay, so one more time, it is worth spending a second here. Let me just leave it here for a second. So, table of Maclaurin series. Yeah, look at it for a second, okay? All right. Awesome. Okay, so let's do some examples. Example number 7 already. Find the Maclaurin series for the function f of x equal to 1 over root of 2 minus x and its radius of convergence. Okay, so check this out. I look at this and it looks complicated, and probably you think there's a reason why she showed that table. So here we go. Let me show it to you, okay? There it is, right? So then out of everything we have, the only thing that looks somewhat familiar or somewhat similar to 1 over root of 2 minus x is the last one, 1 plus x to the kth power. Make this look like 1 plus something to a power that is a real number, okay? So I'm going to take my 1 over root of 2 minus x, and I'm going to take care first of writing that bottom as 1 plus something, okay? In order to do that, I'm going to ignore the square root for a second. I'm going to take 2 out. If I take 2 out, then this becomes 1, so I have my 1 there. And I want to write it as plus something. Well, that something, it's what I get when I pull 2 out of negative x. So this would be negative x divided by 2, and you can check your answer, right? You can verify that if I multiply that 2 by 1, I get 2. If I multiply 2 by negative x over 2, I get negative x, so I'm good to go, okay? Now, I still need to write this as 1 plus something raised to a real number. So let me take that root of 2 out, and then I'm left with 1 over root of 1 plus negative x over 2, which is starting to look like something like what we want, right? This is 1 over root of 2. I'm going to write this as, I'm going to turn this into 1/2, but since it is in the denominator, I'm going to bring it to the top by changing the exponent to negative. So this is what I mean. I'm going to write this as 1 plus negative x divided by 2, the whole thing to the negative 1/2, okay? So check this out. Now I'm multiplying 1 over root of 2 by 1 plus something to a power. So then if I compare my formulas, then this is what appears as x on the table, and this is k on my table. So if I take this information, then I can go back to my table, right, and use this to write the power series, okay, knowing that the absolute value of my something has to be less than 1, okay? This x here is this x here, okay? So whatever I'm adding has to be less than 1 in absolute value, okay? So what do I get? Well, I get that this is equal to, well, I'm going to take the 1 over root of 2 out, and then I get, well, 1, right? The first term is 1 plus k times x, so 1, and then plus k, which is negative 1/2, times the x there, which here is negative x over 2, okay? And then I have to simplify this thing. And then what else do I have? So it's plus k, so then it goes like that. And then I keep replacing, and I get that this is just plus negative 1/2, so k, and then k minus 1 over 2 factorial times my x squared, which is negative 1/2 x, and then squared all the way to infinity, okay? So that's what I get. And then I know that this is the case if the absolute value of negative x divided by 2 is less than 1. Well, this implies that the absolute value of x is less than 2, right? Because I have to multiply by 2. And then this is my radius of convergence. So radius of convergence is 2. All right, so next example. Find the sum of the series that goes n equals 0 to infinity of negative 1 to the n, 3 pi to the 2n over 4 to the 2n, 2n factorial. I look at this and I feel like I have to immediately rewrite this from n equals 0 to infinity, negative 1 to the n over 2n factorial, and then write 3 pi over 4 to the 2n. You see what I'm saying? Like combine these two because they have the same exponent. Now, after I do that, I look at that and it looks like I have my even exponent, okay? I have negative 1 to the n times something to the 2n over 2n factorial. So go back to a little table, right? Go back to a little table, and then here you have that the sum from n equals 0 to infinity of negative 1 to the n something to the 2n over 2n factorial is just cosine of that something. You see what I'm saying? When I mean by something, it's like here, my power series, the power series I have in example number 8 is exactly the same as cosine of x, except that then instead of having x, right, like that, expressed like just x, we're replacing x with 3 pi over 4. So then this is just equal to, cosine of 3 pi over 4. That's it, okay? Now, cosine of 3 pi over 4, you all know it's negative root of 2 over 2. Okay, now if you need to, then write a little note here, right? Because the sum from n equals 0 to infinity of negative 1 to the n of, I'm going to write x in a different color, right? X to the 2n over 2n factorial, it's equal to cosine of x. You see it? Pretty cool, huh? So this is why it's so important to know your expansions, know your Maclaurin and Taylor expansions by heart. Well, not Taylor expansions, but usually the ones that you memorize are the ones centered at 0. In other words, the Maclaurin series. Okay? So now we have to evaluate the integral of e to a negative x squared as an infinite series and then estimate the definite integral correct to within an error of 0.001. Okay. Now, part A, knowing the Maclaurin series or the Maclaurin expansion of e to the x is super helpful because we don't know what the antiderivative of e to the negative x squared is, okay? So I'm going to use the fact that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. Now, just like we did before, you have to be careful, right? This is the expansion of e to the x, but we have e to the negative x squared. So we have to go back to the power series, right? We have to go back to the Maclaurin expansion and replace x with negative x squared. So e to the negative x squared is equal to the sum from n equals 0 to infinity of negative x squared to the n over n factorial. Now, I know that then the integral of e to the negative x squared dx, it's equal to the integral of the sum from n equals 0 to infinity of negative x squared to the n over n factorial dx. And I know that I have to take the antiderivative of x to the 2n, right? So I'm going to get rid of that negative for a second. So I get that this is the sum from n equals 0 to infinity of the integral of, well, negative 1 to the n, x squared to the n, divided by n factorial dx. And then again, you're finding the antiderivative with respect to x. So everything without x, you ignore, okay? So then this is equal to the sum from n equals 0 to infinity of, keep the negative 1 to the n, keep the n factorial, and then the antiderivative of x to the 2n is x to the 2n plus 1 over 2n plus 1. And since I'm computing the indefinite integral, I have to add c. So that is my answer, okay? Now, that was part A. For part B, we have to approximate the definite integral within an error of 0.001. So part B, evaluate 0 to 1, e to a negative x squared dx, correct within an error of 0.01. Okay, perfect. So now, from the previous part, we know that the integral from 0 to 1 of negative x squared dx is just equal to the sum from n equals 0 to infinity of, well, negative 1 to the n over n factorial x to the 2n plus 1 over 2n plus 1 evaluated from 0 to 1, which is equal to the sum from n equals 0 to infinity of negative 1 to the n over n factorial. And then here we have that this is just 1 to the 2n plus 1 divided by 2n plus 1. So this is 1 to the 2n plus 1 minus the same series evaluated at 0. So negative 1 to the n, 0 to the 2n plus 1 over n factorial 2n plus 1, right? Now, notice that this right here is equal to 0 because I'm starting at 0. So 0 to the first power is equal to 0. So I am left with the sum from n equals 0 to infinity of negative 1 to the n over n factorial 2 times n plus 1. Okay, beautiful. So what I'm going to do now is I'm going to use, whenever you see a series with a negative 1 to an exponent, you know that we're dealing with an alternating series. So I'm going to use the alternating estimation theorem, okay? So if I want to use the alternating series estimation theorem, I have to make sure that it actually applies. So I'm going to do this here. So we want to use the alternating series estimation theorem. Oh my God, I'm so lazy. Estimation theorem. Okay, what do I have? We know that given our series, this thing that it's multiplying the negative 1 to the n, this is Bn, okay? So we have that Bn has to be larger than 0. We have that. We have that the limit as n goes to infinity of Bn has to be 0. And Bn is increases because, well, Bn is larger than Bn plus 1, right? Because if you take another term, you will be dividing by something larger, okay? When you substitute n plus 1 here in the denominator. Perfect. Okay. So I can apply the alternating series estimation theorem, and we know how it works, right? S minus Sn is less than or equal to Bn plus 1. So in this case in particular, that tells me that my error is given by Bn plus 1, and we wanted it to be less than 0.001, okay? Therefore, well, what do? B0 is equal to 1. B1 is equal to 1 over 3, which is 0.333. So we're not less than 0.001 yet. B2 is equal to 1 over 10, which is 0.1. B3 it's equal to 1 over 42, which is equal to 0.023. B4 it's equal to 1 over 216, which is equal to 0.005. I'm almost there. B5 it's equal to 1 over 1320, which is equal to 0.0008, and this is less than 0.001, so that tells you you have to stop at B4, okay? Therefore, S4 equal to, well, the sum. So I take the sum from, here we go, I have it here, the sum from n equals 0 to 4, so n equals 0 to 4 of negative 1 to the n of negative 1 to the n over n factorial, so n factorial to n plus 1, it's equal to, well, what do we have? 1 minus 1 over 3 plus 1 over 10 minus 1 over 42 plus 1 over 216. This is approximately equal to 0.747. Accurate within 0.001 according to the alternating series estimation theorem, okay? Now we have to find the first three non-zero terms in the Maclaurin series for e to the x cosine of x, and we know that the Maclaurin series for e to the x and for cosine of x are exact. So we can just use them, right? So e to the x cosine of x, it's equal to, well, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus blah, 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 times the Maclaurin series for cosine of x, we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And then you just multiply it term by term, okay? So since I'm looking for the first three non-zero terms, I'm going to see what happens to the constant term, the linear term, the quadratic term, the cubic term. So the first couple of terms, okay? So first I'm going to multiply 1 by this whole thing. So if I do that, I get that this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus da da da. Then I'm going to see what happens when I multiply x by the whole thing. So if I do that, I get plus x minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th power over 6 factorial plus da da da. Then I'm going to see what happens when I multiply x squared by the whole thing. I get plus x squared over 2 factorial minus x to the 4th over 2 times 2, which is 4, plus x to the 6th over 4 times 3, you get 12 times 2, 24 times 2, you get 48. That's good enough. Then let's see what happens if I multiply x cubed over 3 factorial times this whole thing. When I do that, I get plus x cubed over 3 factorial minus x to the 5th over 3 times 2, you get 6 times 2, you get 12, and so on. Let's see if this is enough, okay? Now, what do I get? I get that this will be equal to, well, I get my constant term, which is 1. I have it here. Then what happens to a linear term? It actually survives, so I have my linear term here, so plus x. Then I'm going to look at the quadratic terms. Well, the quadratic terms here, negative x squared over 2 factorial cancels this x squared over 2 factorial. So let me see what happens to the cubic terms. So I get here, I get negative x cubed over 2 factorial and x cubed over 3 factorial. So x cubed over 3 factorial, well, 3 factorial is 3 times 2, you get 6. And this is 6 minus x cubed over 2. And we get 1 minus 3, it's negative 2 over 6 x cubed, which is the same as negative 1 over 3 x cubed. So here we get negative x cubed over 3, and we have the first 3 non-zero terms in the Maclaurin series for ex cosine of x. Okay, what else do we have? Ooh, very interesting. I think the next two examples we're going to use the Maclaurin expansions to find limits, okay? So here we go. We look at this, and we know from calculus 1 that this is just 1 minus 0 over 0, 0 over 0, so you can L'Hopital it, but in this case, instead of using L'Hopital's rule, we're going to use series, okay? So we know the power series, we know the Maclaurin expansion of e to the x, so this is the limit as x goes to 0 of, well, the Maclaurin expansion of e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial, which is 6, plus da da da, all the way to infinity. Then minus 1 minus x all over x squared. This is equal to the limit as x goes to 0 of, cancel 1 and 1, cancel x, and you're left with x squared over 2 plus x cubed over 6 plus da 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 over x squared, but you can cancel this a little bit more, and you get that this is x squared divided by x squared, you get 1/2 plus x over 6 plus a bunch of terms with x in them, so they all go to 0 as x goes to 0. Well, that tells me that this whole thing goes to 0, so my limit is 1/2, okay? Now we have to evaluate the limit as x goes to 0 of tangent of x minus x over x cubed, and we're going to follow the same approach, okay? We're going to go back to the table and use the expansion of tangent of x. Well, the expansion of tangent of x is, you can find it by actually dividing the Maclaurin series of sine by the Maclaurin series of cosine, okay? And you'll get that this is just x plus x cubed over 3 minus x to the 5th over 5 all the way to infinity minus x all over x cubed. So then I get that this is the limit as x goes to 0. Simplify x and x. Divide everything by x cubed, and you're left with 1 over 3 minus x squared over 5 plus a bunch of terms that go to 0 as x goes to 0. So my final answer for this limit is 1 over 3, okay? One last example, we have to find the Taylor series for f of x equals e to the x at a equals 3. And keep in mind that whenever we are finding the Taylor series, right, or we're finding the Taylor expansion of a function at a equals 0, then we call it the Maclaurin series. So Maclaurin, one more time, Maclaurin means a is equal to 0. The steps are the same, the formula is the same, the coefficients are the same, okay? Now, sometimes, since this is something happening really, this is super local, okay? If I'm approximating my function at a equals 0, or in this case at a equals 3, that means that my approximation is good for values of x really close to my center, okay? So then, for example, you can have a function that you want to approximate your function at x equals 100. So maybe centering the function at 0, it's not accurate enough, okay? So then this is just to remind you what this is. Remember that the formula goes sum from n equal to 0 to infinity. You take the nth derivative, evaluate at a, x minus a to the nth power over n factorial. So in this case, if we replace a with 3, then the nth derivative of my function f of x evaluated at 3 is just e cubed, okay? And then, well, x minus 3 over 3 factorial, okay? Well, x minus 3 to the nth power over 3 factorial. And this is what it looks like, okay? It's still, the more terms you add, the better your approximation is, okay? So here you have a Taylor polynomial of degree 2. If you add one more term, you have a Taylor polynomial of degree 3. We're just approximating the function using polynomials, okay? If you let it go to infinity, then you get the function. That's all I have for section 8.7. Bye-bye.